Welcome you all in the lecture number 17 of Abstract Algebra MTL 6051. In previous lecture, we already discussed about the normal series of a group, right? Composition series of a group, and examples related to normal series and composition series. And at last we discussed about a group G possesses more than one composition series. More than one composition series. Okay. Then a natural question arises that if group possesses more than one composition series, then what is the relation between those composition series, right? Related to this question, answer is given by Jordan Hölder, right? Now in today's class we will discuss about the Jordan-Hölder theorem. Okay. See, the Jordan-Hölder theorem says that if any group has two or more than two composition series, then they are equivalent. What it means? It means that suppose G be a group, and what is G? G is group. Okay. Then we are talking about finite group. Remember that G is group, and this C1 is one composition series, C2 is another composition series, C1 and C2. The C1 is E N0, E is N0, subset of N1, right? This is N2. Basically N0, N1, N2, Nt are subgroup of G. Okay, then this is the sequence of subgroup. Basically it is the sequence of subgroup. Okay, this is another sequence of subgroups, right? Then this equation 1 and 2 are the composition series. Then if 1 and 2 are different composition series, then they are equivalent. What do you mean by equivalent? If 1 and 2 are composition series of a finite group G, then there exists a 1-1 onto map from factor group of 1 to factor group of 2. Okay, there exists a 1-1 onto mapping between factor group of 1 and 2. Okay, then 1 and 2 is said to be equivalent composition series, or in other way we can say that the length of composition series are equal. What is the length of first series? Total number of terms is t plus 1 excluding G, that is Nt. Total number of term is t. In second series, total number of term is m, right? The first condition that length of those composition series are equal. Okay, and there exists isomorphism between the factor group of 1 and 2. Okay, then these two series C1 and C2 are equivalent. Okay, so either use this definition or this definition, both are same. Okay, then what is the conclusion? That two composition series of a finite group G are equivalent if there exists a 1-1 onto mapping between factor group of 1 and 2. Okay, now see the statement of Jordan-Hölder. If G be a finite group, remember that this theorem is applicable for the finite group only. If G is finite group and this is one composition series, and this one is another composition series, then these two composition series are equivalent. Jordan-Hölder theorem says that if a finite group has two composition series, then this composition series are equivalent. What do you mean by equivalent? We already defined. Length of composition series are equal, means m is equal to t, first condition, and there exists isomorphism, right? Isomorphism means 1 1 onto mapping, right? Which we call it permutation 1 1 onto map. From I to I dash means factor group of first, that is ni plus 1 by ni is isomorphic to hi dash plus 1 by hi dash. Okay, then these two composition series are equivalent. Okay, now see the proof of Jordan-Hölder theorem. Okay, how we will prove it? We apply the method of induction. Okay, method of induction on the order of group. What is order of G? Order of G is finite. It is given on the in the statement of the Jordan-Hölder theorem. What is order of G? Order of G is finite. Apply method of induction on this order of G. Okay. If n is equal to 2, we start from n equal to 2. Since we know that composition series, right? For the composition series, group must contain at least 2 elements. Then, if n is equal to 2, that is order of G is equal to 2, then this G has a composition series E, that is G0, subgroup of G1, that is G, this composition series. And this is only composition series of this G whose order is 2. Okay. So by method of induction, right, G has only one composition series. This is only one composition series. The result is true. Okay, in this case, only one series. This series is equivalent to itself. Okay, no problem. Now, by method of induction, we can assume that this result is hold. Right? Means result is true for all group. Result holds are true for all groups whose order is less than order of G. Suppose if n is subgroup of G, order of n is less than order of G, then if there exist two composition series of n, then they are equivalent. Okay, then they are equivalent. Next, case first. How we will prove it? Since there are two composition series of G, n0, n1, n2 up to nt of G, and next one is h0, h1, h2, hm, that is G. These are the two composition series, right? What is nt minus 1 and hm minus 1? Nt minus 1, hm minus 1. These nt minus 1 and hm minus 1 are maximal normal subgroup of G. Then there are two cases arises. Nt minus 1 can be equal to hm minus 1, or Nt minus 1 cannot be equal to hm minus 1. Okay, either this thing happen or this happen. It means this Nt minus 1, either this is equal to this or not equal to this. So consider the case first. If Nt minus 1 equal to hm minus 1. Okay, see, let us consider case first. Nt minus 1 is equal to hm minus 1. Okay, then what happened? What is Nt minus 1? Nt minus 1 is subgroup of G, that is order of nt minus 1 is less than order of g. By method of induction, there exists a composition series of nt minus 1. Okay, there exists a composition series of nt minus 1, and there exists a composition series of hm minus 1. Okay, since nt minus 1 and hm minus 1 are equal, it means the nt minus 1 and nt minus 1 has composition series this, and hm minus 1, which is equal to nt minus 1 by case first, has composition series this, right? By method of induction, they are equivalent. They are equivalent means what? T minus 1, that is length is equal to m minus 1. What is this? T is equal to m, means T is equal to m, and their factor group are isomorphic, right? Since they are equivalent by method of induction, right? By induction hypothesis, that 3 and 4 are equivalent, so T is equal to m, right? And factor of 3 and 4 are isomorphic, right? So this series, this composition series are equivalent. Okay, these are equivalent. Now one terms is same, which for equivalency this term is only we have to show that is what is nt upon nt minus 1. What is nt? Nt is g by nt minus 1. What is g? G is hm, right? From second series. What is nt minus 1? That is hm minus 1, right? From case 1. Then nt minus 1 is isomorphic, nt by nt minus 1, this factor group is isomorphic to hm by hm minus 1. Okay, so all the factors means n0, n1 up to nt minus 1, h0, h1, hm minus 1, right, up to here, their factor are equivalent. Their factor are equivalent. Okay, so what about the nt by nt minus 1 and hm by hm minus 1? Here we already shown that they are equivalent. Since these are equivalent, this factor and this factor are equivalent by method of induction, and this are equivalent, we prove it here. So all the factors, factor of 1 and factor of 2 are isomorphic to each other. Okay, it means 1 and 2 are equivalent if nt minus 1 equal to hm minus 1. If this thing happen, then these two composition series means 1 and 2 are equivalent. Okay, now consider case 2. If they are not equal, then what happen? See, if nt minus 1 does not equal to hm minus 1, then we already studied one theorem that h and k are two distinct normal subgroup of G, right? Are two distinct maximal normal subgroup, maximal normal subgroup of G, right? Then their intersection H intersection K is also normal subgroup of H and K, right? And HK by H is isomorphic to K by H intersection K, right? This is second isomorphous theorem, and this is one another theorem, right? We already proved this thing in our previous class. Now see, if nt minus 1 does not equal to hm minus 1, then what? Let us consider k. What is k? K is nt minus 1 intersection hm minus 1. Okay. What is k? K is finite group, right? What is k? K is finite group. Then what is the order of k? don't know, but order of k is less than order of g. What method of induction says that the result is true for all the groups whose order is less than order of g. Since order of k is less than order of g, therefore there exists a composition series for k. What is that composition series? Let us consider this composition series k0, k1, k2 up to ks. Okay, this is the composition series, right? Then what is k? K is nt minus 1 intersection hm minus 1. That is k is subgroup of hm minus 1 as well as ant minus 1. What is nt minus 1 and hm minus 1? These are the maximal normal subgroup. Okay, maximal normal subgroup of G. Then apply our previous theorem. Okay, apply our previous theorem later on. See, K is equal to nt minus 1 intersection hm minus 1. Then k0, k1, k2, ks. Okay, this is the composition series of k. Now what is ks? ks is k. What is ks? Ks is basically k. And what is k? K is nt minus 1 intersection hm minus 1. It means k is subgroup of nt minus 1 as well as k is subgroup of hm minus 1. Ks is subgroup of nt minus 1. And nt minus 1 is subgroup of G, that is nt. Similarly, k0, k1, k2 to ks, hm minus 1, that is hm, that is G. See these two series, 5 and 6, right? Remember that what is the length of 5? Length of 5 is s plus 2. Why s plus 2? See here. How many terms from here to here? S plus 1. And one more term, nt minus 1. So s plus 1 term plus 1 term, right? And be excluding at the time of counting the length, at the time of evaluating the length, we exclude the group itself. So excluding this one, what is the length? Length is s plus 2. Similarly, what is length of 6? S plus 2. From here to here, s plus 1 term. So length of this 5 and 6 is s plus 2. Okay. Now see, these two composition series 5 and 6, whether they are equivalent. These 5 and 6 are equivalent. For 5 and 6 they are equivalent if their length are same. Since their length is s plus 2 and s plus 2 both are equal, so one condition is satisfied. Length of composition series is equal. But what about the isomorphism between the factor of group? See, for this series, this one up to this one, right? Their factor group are isomorphism. Their factor group are isomorphism, right? Factor group of this series and this series are isomorphic to each other. Okay. Now apply the second condition. Previous theorem. What is the previous theorem? If nt minus 1 and hm minus 1 is maximal normal subgroup of G, then nt minus 1, hm minus 1, right, by hm minus 1 is isomorphic to nt minus 1 by nt minus 1 intersection hm minus 1, or hm minus 1 by nt minus 1 intersection hm minus 1, means hk by h is isomorphic to k by H intersection K, right? This thing. What is this? This is second isomorphism theorem. Second isomorphism theorem, right? We already proved this theorem in our previous lecture. Now see, apply this theorem and prove that factor group of 5 and factor group of 6 are equivalent, right? So factor group up to this term are equivalent, right? No need to worry about what about the factor group of these terms. Factor group of these terms are equivalent. Remaining term, what we have to prove that this factor group, these factor groups of two series are equivalent or not. Let's see. What is nt minus 1 by k, right? Nt minus 1 by k. Nt minus 1 intersection hm minus 1, right? This. Then if this is composition series, see k0, k1, k2 up to ks, or ks is k, nt minus 1, nt is g, and k0, k1, k2, ks, hm minus 1, hm is g. Then factor group up to this term are equivalent. Okay. Then nt minus 1 by k, this is one factor group, and nt by nt minus 1 is another factor group, and from second series hm minus 1 by k is one factor group, and hm upon hm minus 1 is another factor. Okay. Since these two series are composition series, so these factor group are simple, right? Simple. By definition of composition series, these factor group are simple. Now we have to prove that the factor group, this factor group is isomorphic to some one of these two. This factor group is isomorphic to either this or this, and this factor group is isomorphic to either this or this. Okay. How we will prove it? We apply the second isomorphism theorem. Okay. Now see, what is second isomorphism theorem and how we apply it? What is nt minus 1 and hm minus 1? Nt minus 1 and hm minus 1 are maximal normal subgroup. Nt minus 1, hm minus 1 are maximal normal subgroup of G. Nt minus 1, hm minus 1 are maximal normal subgroup of G. Okay. Then by second isomorphism theorem, this nt minus 1, right, means nt minus 1 intersection hm minus 1 is isomorphic to hm minus 1 into nt minus 1 by hm minus 1. But what is this? This is G. How? We already proved one theorem, right, in our previous lecture. If hm minus 1 and nt minus 1 are maximal normal subgroup, then their product is equal to G. Then this is equal to G by hm minus 1. This is G by hm minus 1. This G by hm minus 1 is isomorphic to this term. Similarly, hm minus 1 by nt minus 1 intersection hm minus 1 is isomorphic to this term, right? Now combine these two. See, G by hm minus 1 is hm by hm minus 1, and nt minus 1 The nt minus 1 intersection hm minus 1. What is this? This is k. This is nothing but k. Right? This is equal. So g by hm minus 1 is simple. What is this? This is simple. Okay. And since g by hm minus 1 is isomorphic to nt minus 1 by k. What is this? This is simple. If this is isomorphic to nt minus 1 by k, then this is also simple. Okay. Similarly, g by nt minus 1 is isomorphic to hm minus 1 by k. What is g by nt minus 1? This is simple. And this is isomorphic to hm minus 1 by k. So this is simple. Right? Since this is isomorphic to this, therefore this factor group is also simple group. It means these two factor group are simple group. Okay. Next, is these factor group are isomorphic? See, nt minus 1 by k is isomorphic to this thing, g by hm minus 1. Already we proved it. And nt by nt minus 1 is isomorphic to this thing. It means the factor group of 5 and 6, series 5 and 6 are isomorphic. Right? What is the length of 5 and 6? That is s plus 2. We already seen it. What is 1 and 5? 1 and 5 are isomorphic. Why 1 and 5 are isomorphic? What is 1? 1 is n0, n1, n2, ent minus 1, ent equal to g. This is 1. And what is 5? 5 is k0, k1, k2, ks, subgroup of nt minus 1, ent is equal to g. Okay, this is 5. Now see 1 and 5. 1 and 5 are two composition series of ent. This is ent. Okay, this is two composition series of ent. What is the previous term of nt? That is nt minus 1. Okay, previous term of nt is nt minus 1. And what is previous term of this nt? Nt minus 1. And in case first, we already proved that if these two terms are equal, means nt minus 1 equal to hm minus 1, here both are equal, nt minus 1, nt minus 1. Then if these two terms are equal, then composition series are equivalent. Right? So I write here in case first, right? Second last term equal to nt minus 1, both are same. Right? Therefore, by case first, these two series 1 and 5, right? This series and this series both are equivalent, means series 1 and 5 are equivalent, right? Series 1 and 5 are equivalent. 1 is equivalent to 5, and we already proved that 5 is equivalent to 6, right? What is 6? You can write 6 here, k0, k1, k2, ks, hm minus 1, hm, g, right? This thing. So this is what? This is composition series of hm, that is g, right? Which is different from 5, and we call it equation number 6. Okay, call it equation number 6. And what is 2? 2 is h0, h1, h2, hm minus 1, hm, that is g. This is 2. Now see, second last term. What is second last term? Second last term is hm minus 1, and here hm minus 1. Both are equal. Both are equal, then 2 and 6, by case first, 2 and 6 are equivalent. It means 2 equivalent to 6. Right? Now apply the transitive relation. What is 1? 1 is equivalent to 5. Okay, 5 is equivalent to 6. 1 is equivalent to 5. 5 is equivalent to 6 implies that 1 is equivalent to 6. Okay, since 2 is equivalent to 6, 1 is also equivalent to, it means 1 is equivalent to 2. What is 1? 1 is composition series, first composition series, that is this one. Okay, what is 2? 2 is this composition series. Right? These two series are finite group G. So 1 and 2 are equivalent. Okay, this is the complete proof of Jordan-Hölder theorem. Okay?